Welcome to the third and last video lecture for the first week of the MPP Calculus course. This lecture will be focused on the rules of differentiation. Now, in the conceptual lecture, we talked about the formal definition of the derivative as this limit. In practice, no one uses this definition to calculate a derivative. So with that in mind, we're going to focus this class, rather than spending a lot of time on limits, we will instead focus on the basically shortcuts that most people use when they are actually calculating derivatives. The first of those rules is simply regarding a constant. So if you have a derivative and you're trying to take a derivative of some constant c, that derivative is simply 0. I'd do a bunch of examples, but I don't think I need to. The derivative of 5 is 0, the derivative of 25 is 0. The derivative of a parameter a, which we take as given, that's not variable, is 0. If you have a function of the form x to the n power, the way that you take its derivative is by bringing the power down and turning it into a coefficient, and then subtracting 1 from the power. So just to give you a few examples of this, if you have x to the 5th, it becomes its derivative d dx is 5x to the 4th. If you have x to the 20th, its derivative becomes 20x to the 19th. If you have x to the 1st, its derivative becomes 1 times x to the 0, which is just 1. I won't bother to do many more examples of that type, but it's worth noting that I haven't placed any limits really on this exponent n. So this is the power rule, which is what this is really very flexible. So if you have some function f of x that is the square root of x, you know from algebra that you can express that as x to the 1/2. You can then take the derivative of that by taking the 1/2 down in front, 1/2, and subtracting 1 from the 1/2, you get negative 1/2. And this rule basically works for any function, any power. So if you have the function f of x is equal to x to the 7/10, for example, well, its derivative is just going to be 7/10 times x to the 7/10 minus 1, which would be the negative 3/10, and so forth. So now you go ahead and try. I'm going to just write a few other functions here. You try taking their derivatives using the power rule. I'm going to pause and go ahead and pause the video while you do after I'm done writing, and then come on back. All right, so the first is very straightforward, 2x to the 1st power. The second, we put 3/2 out front, subtract 1 from 3/2, we get 1/2. Here, same basic idea, we take 5/4, subtract 1, we get 1/4. The nice thing again, the power rule works on negative numbers. You apply it in exactly the same way. We're still subtracting 1 from the power. So in this case, it gets smaller by 1. Its absolute value increases. So it goes from -3 to -4. Same basic procedure applies here. We have negative 1/8 out front. We have x, and if I subtract 8/8, I get negative 9/8. So when you have a negative power, the absolute value of the power on the derivative is actually going to be getting bigger rather than getting smaller. If we have a constant in front of our power, basically the constant just sort of sticks around. So if I have some derivative that I'm trying to take that is of the form of a constant times a power, it's basically the same thing. You just sort of leave the constant out there. So you have c times n and then x raised to the power n minus 1. So for example, if you have 3x to the 5th, it becomes 5 times 3x to the 4th, or 15x to the 4th. If you have 8x to the 1/2, it becomes 8 times 1/2, or 8 over 2, x to the negative 1/2. If you have x to the negative 3 over 4, the 1/4 stays there, so you have negative 3 divided by 4 times x to the negative 4th power. There we've subtracted 1 from the negative 3, and so forth. So you basically just treat constants in front of the powers. If they're being multiplied by x raised to a power, the constant just stays there throughout the differentiation. The nice thing about polynomials is that polynomials, if you're taking their derivative, are simply a series of terms that look something like this. So if you have a polynomial that is added together, so I might have ax to the n plus bx to the m plus cx to the r, whatever it is. I can take the derivative by simply taking the derivative of each of the terms separately. So my derivative would be a times n, x raised to the n minus 1, plus b times m, x raised to the m minus 1, plus c times r, x raised to the r minus 1. So you'll notice the first term is simply the derivative of the first term. The second term is the derivative of the second term. The third term is the derivative of the third term. Also notice I could have had a negative number here for the constant, and that negative sign would be preserved. So if you have something, just as an example, if you have a function that is x to the 4th minus 3x squared, the negative sign persists. When you take the derivative, you take the derivative of the first part, you bring the 4 down, x raised to the 3rd power. You keep the negative sign, minus, I take 3 times 2 and get 6, x to the 1st power, which is implied. So polynomials are very nice in that sense, that anytime you have addition or subtraction, you can just take the derivatives of the terms separately. I do want you to be a little bit careful. If you, on the other hand, have a denominator, you're not allowed to use this process. So if you had a function, say you had the function f of x that was equal to x to the 4th minus 3x squared over x minus 1, you're not allowed to take the derivative of the two terms separately, because everything in the top is divided by everything on the bottom. Okay, you could split it up into two different fractions. You could say x to the 4th over x minus 1, remembering that the denominator stays constant, minus 3x squared over x minus 1. So there you could take the derivative of this first term minus the derivative of the second term, but you have to keep the denominator present through the whole thing. Now I'm going to write this polynomial rule a little bit more generally, because it does actually apply anytime you're adding or subtracting terms together. So you can think about a polynomial as being the sum of several different functions. And if you're taking their derivatives, all you do is you take the derivative of the first term plus or minus whatever you started off with, the derivative of the second term. Now, dealing with addition and subtraction is relatively straightforward. Unfortunately, dealing with multiplication and division is not. For multiplication, if you want to take the derivative of two functions multiplied together, what you need to do is you take the derivative of the first function and you multiply it by the second function, not its derivative. And then you add to that the original function times the derivative of the second function. Notice it doesn't matter which order you do them in which order you do them. It's the derivative of the first times the second plus the derivative plus the first times the derivative of the second. This is something that's a lot easier to see through examples, so let's go ahead and do a few. All right, so in this case, we're going to use the rule we just saw, which was the product rule. In practice, if you end up seeing these, quite honestly, I would encourage you to multiply them out. It will give you the same derivative if you do that, and I think that people make fewer mistakes doing the derivative of a polynomial than they do using the product rule. But for the sake of illustration, we'll use the product rule here. So we need the first term, we need the derivative of the first term. Well, the derivative of x is 1 and the derivative of 1 is 0. So the derivative of the first term would be 1 times the second term unchanged plus the first term times the derivative of the second. Now the derivative of the second, this first term, its derivative will be 2x. The second term is a constant, so that disappears. So if I want to, I can multiply that out. I get x squared minus 1 plus 2x squared plus 2x. And you can combine that to get 3x squared plus 2x minus 1, which should be the same thing that you get if you FOIL out these terms. Same basic idea for the second function. If I want to take its derivative, I need to take the derivative of the first term, its derivative we saw before was 1, times the second term, plus the derivative of the second term, which would be 5x to the fourth, times the first term unchanged. Now, I want you to notice that if I had a negative power here, I could use the same rule. So let's say that I have h of x. If I instead had x plus 1 divided by x to the fifth, I can rewrite that to be x plus 1 times x to the negative fifth. So if I want to take its derivative, I can use the product rule here. I just need to pay careful attention to how I treat this negative sign. So again, I take the derivative of the first term is 1. I take the second term unchanged, x to the negative fifth, plus I take the first term unchanged, and the derivative of x to the negative fifth is going to be negative 5x to the negative sixth. So I now have the full derivative that I could write out if I wanted to, x to the negative fifth, and I can distribute this across. I get negative 5x to the negative fifth minus 5x to the negative sixth, which I can simplify to be negative 4x to the negative fifth minus 5x to the negative sixth, which is the same thing that I would get if I distributed this across and took the derivative of the polynomial. The reason that I point that out is that very often you'll see that there is a quotient rule that you can use if you prefer it, if you find it easier, and I'll go ahead and show it to you in just a moment. But if you forget what the quotient rule is, this process that I just used works. So if you can correctly remember the product rule, which doesn't have any subtraction in it, as long as you keep track of the negative sign correctly, you will be able to apply it correctly. So here's the formal version of the quotient rule. If you have two functions divided by one another, you take the derivative of the first times the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over the denominator squared. So let's go ahead and see how that would work on the function that we just saw. Okay, so here is the function we tried last time. The derivative of the numerator is 1. The denominator unchanged is x to the fifth minus the numerator, x plus 1, times the derivative of the denominator, 5x to the fourth, over quantity. This should be x to the 5th squared, which is x to the 10th. Okay, so simplifying that, I get x to the 5th minus, distributing across, 5x to the 5th minus 5x to the 4th over quantity x to the 10th. Now, remember that when you're dividing, you're going to subtract the exponents. So in the end, my exponent, or my expression ends up being, I take the first, this first term is negative 4x to the 5th divided by x to the 10th becomes negative 4x to the negative 5th. And this last term divided by 10 becomes 4 minus 10 is negative 6 minus 5x to the negative 6. So you see, you get the same answer, but it requires remembering this formula or having it on your cheat sheet for the exam. But I typically find it easier to do this way. There's no requirement that you do. So here we have the rules of differentiation that we're going to be using for this week. Next week, we will be doing the chain rule. We will be doing differentiating exponential functions. So be warned that in class, or in this lecture, we've talked about x raised to a constant power. We've not talked about a constant raised to x power. Taking the derivative of that is a little bit different. So before we wrap up, I'm going to put up a set of example problems. I'll encourage you to pause the video and try them out. All right, so starting with the first one, we are going to take the derivative f prime of x. We take the derivative of the first term is 2x, of the second term is negative 2. For the third term, we bring the exponent down. We subtract 1. For the final term, we bring the exponent down, so that's negative 8 times negative 1, x to the negative 2. If you want to, you can simplify that a little bit more. You get 2x minus 2 minus 3 halves x to the negative 5 halves plus 8 x to the negative 2. You could move these items with negative exponents into the denominators if you wanted to. For the second one, we get, again, we're going to just do each term separately. So I bring the negative 2 down. Negative 2 times 5 is negative 10x. I subtract 1, I get negative 3. For this second term, I'm going to treat it as negative 8x to the negative 1. It's the same basic scenario as I had in the previous question. I have plus 8x to the negative 2 for that term, and then plus 0 for the constant term, or just 10x to the negative 3 plus 8x to the negative 2. You could also write it 10 over x cubed plus 8 over x squared. For this last one, I'll go ahead and use the quotient rule. Really, either way would work. So the derivative of of the function h is going to be the derivative of the numerator, 2, times the denominator unchanged, minus the numerator unchanged, times the derivative of the denominator, over quantity, the denominator, squared. So I can multiply everything out here. I get 2x minus 2 minus 2x plus 3 over x minus 1 squared. My 2 x's cancel out. Sorry, that should have been a negative 3, not a positive 3, because the negative sign distributed. I get that the numerator is negative 5 and the denominator is x minus 1 squared. In this case, it's possible the quotient rule was actually easier. It's sort of 6 of one and a half dozen of the other. All right, so that brings us to the end of the lectures for this week. We will do a bunch more practice problems in class.
So I'll see you there.